Hello, we will see polar plot today. What is a polar plot? Polar plot is a frequency response plot which shows the plot of magnitude of Gj omega versus angle Gj omega. That means magnitude for versus phase as omega varying from 0 to infinity. When we did Bode plot, we did magnitude plot separately and phase plots separately, and both together comprise my frequency response. So here in one plot we get the frequency response for the entire range of omega in one graph. And the disadvantage with this plot is it doesn't give me the individual contribution of each factor. When we do Bode plot, we get the individual contribution of each factor and then we add it up to get the complete frequency response. Now this is an example of a polar plot for some transfer function. So what we have to do is omega equal to 0. What is the magnitude? So here omega equal to 0, the magnitude is infinity. So when we say about the angle, when I take the angle in the counterclockwise direction, the angle is taken as positive. When I take it in this direction, the angle is negative. When we have a pole, obviously the angle will be negative. So whatever the angle, I'll take it in the counter and clockwise direction. So this is my minus 90, this is my minus 90, this is my minus 180, and this is my minus 270. So minus 270 and plus 90 are the same, like that. When I say in the counterclockwise direction, this is plus 90, this is plus 180, this is my plus 270. Or here if I do in the clockwise direction, minus 90, minus 180 and minus 270. So here at infinity, that is when omega equal to infinity, the magnitude is 0 and angle is minus 270. That's why it comes like this. And to get this point, that is cutting the polar plot, cutting the real axis, how we can do is we will have a number which is in terms of real part and j omega part. So equating at this point we know that j omega part is 0. So equating the j omega part equal to 0, we can get the cutting with the real part. Now consider the integral and derivative factor. It can be a j omega in the numerator or denominator of the transfer function. When it is in the denominator, it is a pole at origin. When it is in the numerator, it is a 0 at origin. So when I am having a pole at origin, the magnitude is 1 by omega and the angle is minus 90. So putting omega equal to 0 and infinity, we can get the polar plot. So when omega equal to 0, the magnitude is infinity, and omega equal to infinity, magnitude is 0. So that means the angle is minus 90 when it is a pole at origin. So the polar plot will be entire j omega axis in the negative direction. Same with polar plot for a pole at 0 at origin. It will be Gj omega equal to j omega. It will be an entire positive j omega axis. Now first order factor 1 plus j omega t, either in the numerator or in the denominator. If it is a 0, it will be in the numerator. Otherwise, it will be a denominator. So when I have a pole, simple pole, it is 1 by 1 plus j omega t. So the magnitude is 1 upon square root of 1 plus omega squared plus t squared, and the angle is minus tan inverse omega t because it's a pole. And when omega equal to 0, the magnitude is 1 and angle is 0. When omega equal to infinity, the magnitude is 0 and the angle is minus 90. So omega equal to 0, the magnitude is 1. So I'll take on my real axis 1 and angle is 0. So this is my 0 axis. And at omega equal to infinity, the magnitude is 0 but the angle is minus 90. So this is my minus 90. So it will be a semicircle. And for clarity, I'll find one point in between. I'll take omega equal to 1 by t. That is same as omega t equal to 1. My magnitude will be 1 by root 2 and the angle will be minus 45. So I'll draw a vector 1 by root 2 at an angle 45. Minus 45. So this will be that one. So I got this in between point. So this is the real part and this is the imaginary part of the transfer function. So what I do is multiply the numerator and denominator by the complex conjugate 1 minus j omega t and 1 minus j omega t. So denominator will be 1 plus omega squared t squared and I'll get a term 1, it will be 1 plus j omega t upon 1 plus omega squared t squared. So 1 by the real part will be this and the j part will be this. So that is how we can separate out the real part and imaginary part. Now if it is a first order 0, 1 plus j omega t, normally our control system will not have a symbol 0 like that, but when I take a complete transfer function, it can be a factor in that. What all I am saying is not the complete transfer function. If I have a factor like that in the transfer function, that will be the polar plot. So when omega equal to 0, it is 1 angle 0. When omega equal to infinity, infinity angle 90. So 90 means minus 270. So if I take 90 this direction, so it will be this. So omega equal to 0, 1 and omega equal to infinity, infinity angle 90. So for clarity, I took a point in between 1 by t. The magnitude is root 2 and angle is 45. So I'll draw a vector from here to here. This is my 1 by root 2 angle 45. So that is how we can do this. Now we add a pole at origin to the previous transfer function and upon 1 plus j omega t. So I have 1 by j omega into 1 plus j omega t. So when I have omega equal to 0, it is infinity angle minus 90 and omega equal to infinity, it is 0 angle minus 180. Because when omega equal to 0, no contribution of angle by this factor, only minus 90 of this. And when it is infinity, this gives a minus 90 and this also gives a minus 90. So the polar plot will be like this. Now I'll take a factor, two poles, 1 by 1 plus j omega t1 and 1 plus j omega t2. So when I take the magnitude at omega equal to 0, it will be 1 and the angle will be 0. Both will contribute 0 angle, so it will be 0. When it is infinity, 1 upon infinity will be 0 and a minus 90 by this factor and minus 90 by this factor gives me 0 angle minus 180. Now this will be the nature of the polar plot. That is at omega equal to 0, I have a magnitude 1 and omega equal to infinity, magnitude 0 but angle is 180, minus 180. So that angle is this. So it will cross the j omega axis and come like this. So now how will I find the point which cuts the j omega axis? So what we have to do is rationalize your transfer function by multiplying numerator and denominator by the conjugate, that is 1 minus j omega t1 and 1 minus j omega t2. I separated out the real part and imaginary part. You can verify it by doing it yourself. Now the place at which the polar plot cuts the j omega axis is this point, and that time the real part is 0. So when we come here, I equate the real part equal to 0 and solve for omega. I got omega as 1 by square root of t1 into t2. So putting that in the magnitude of gj omega, or gj omega at omega equal to square root 1 upon square root of t1 t2, I get it as square root of t1 t2 upon t1 plus t2, that is this. Now for this, I added another pole along with the previous transfer function. So when omega equal to 0, this, when I rationalize it, I got this way, that is a real part and a j part. When I put omega equal to 0, it is minus, which is infinity angle minus 90, and it is infinity, it is 0 angle minus 270. So this will be the, this is minus 90. So 270 means this one. So that's why it is crossing the real axis and coming over here. Yes. This is the polar plot of the transfer function given. So this is how we can draw the polar plots. Thank you.